And now we're going to continue with the expression, the synthetic expression. Okay. This week we'll try not to finish narrow escape and diastrate. I'll explain what it means. And starting next week, we're going to go to biology. Application, models, deconvolutions, how we use polymer models to calculate looping time, which is important for the nucleus organization. Chromatin dynamics, double-strand DNA break. Also, we'll continue with aggregation. How you do aggregation with a finite number of particles. This is important for yeast organization, where you have the end of the chromosome, which are called the telomere. You have 32 of them, and they can form clusters. And the clusters, you are interested in how many clusters do you have, and why do you have clusters, and how many particles per clusters, and what's the probability that you find two particles in the same cluster. Again, the novelty here is because you have 32 particles. You have finite numbers of particles. All right, so this is going to be, after this class, this is going to be the second part of the class, which is applications. All right, so but today, this is also a very important part for the application, because this is a coarse graining of rare event. How you quantify rare event? By the narrow escape problem. So narrow escape, or sometimes we call it stochastic narrow escape. So this is what we started last week, and we said the question is, if we have a domain, if you have a particle starting at position x, you ask how long it takes for this particle to find for the first time, to hit for the first time this part here and to find a small hole. This is the goal of the lecture of today, which is how long it takes to find this small hole. Right? So we can start with a full stochastic equations. B of x sigma x w dot. This is a deterministic drift. This is the noise part. We can put the deterministic drift to 0, and then you have purely diffusion. Sometimes you can have what's called degenerated diffusion, and this is very tough. When you have, let's say, for example, diffusion in only one direction. This leads to a completely different type of problem. This is called, this leads in partial differential equation to hypoelliptic operator. And I'm not going to enter into this, because then the problem of escape, when you have noise in only one direction, which can happen if you have devices such as a radio or receiver, you can have only noise in one direction. You want to make sure that noise propagates enough in the system to allow you, for example, to escape. You know, if you want to escape here and you have noise in only this direction, there is no way that you can go that direction. So this is the idea of this condition on the hypoelliptic operator, which I'm not going to go into. But so it happened that you have this. This is, for example, if you think about the Langevin equation, when you write it in 2D, you have noise in only one variable, not in the other one.
Well, here is also 2D, the example.
This is 2D, yeah. And we have noise in two directions. So sigma x here is going to be, the eigenvalues are never going to be 0.
Okay.
So, right, so this is close to identity, or the determinant of this is never 0, right? So, for example, I can give you two open questions for those of you who are interested. The first open question that, so let me state first the problem, and I'll give you two open questions. Two open questions means possible papers, because nobody knows how to solve, including me. I mean, we have to think about it. So let's first formulate the question. If you have pure Brownian motion, right? So let's say you have square x dot equals square root of 2d w dot. This is Brownian motion. This is diffusion coefficient, which can be 1 if you're a mathematician. It's unimportant as long as it is not 0 and positive. Then, how you formulate the time? So we said that the first time tau, depending on x, that your particle, which is satisfy this stochastic equation, the first time that you will hit the absorbing part, which is in here, this is the absorbing boundary, and this is called the reflecting boundary, where at each time the particle hits this, it is reflected. So the first time that you hit this condition, that at time 0, you started at position x. And what you are interested in is you start in here, you look at one example, it arrives here, you average over all the realization, which means the expectation of tau of x. And what is interesting is that u of x, here, which is tau of x, satisfy the equation d Laplacian u. We have seen this 3 or 4 classes ago. This is called the Dynkin equation that were formulated in 1961. D Laplacian u equal -1 for all x in the domain omega, and u of x equals 0 for x in the omega, and du dn equals 0 for x on the reflecting part. This is absorption, and this is reflection. Okay, and so it's hopeless to think that we can have an asymptotic here expansion unless epsilon, the size of the domain, which is absorbing divided by the total boundary. So you take this region here, you divide by the entire boundary length or surface, depends where you are. So if this is very small, let's say 10%, we expect that we can have an expansion for this as epsilon is small. And actually, as we said last week, when epsilon goes to 0, the time should go to infinity, because the time, and the question is how it goes to infinity. This is exactly what we would like to solve. So how it blows up to infinity, this is the goal. And we said we wanted to explore more about how the solution looks like. We said that if you start exactly here on the boundary or in the small neighborhood of this, so let me make here a bigger absorbing boundary. I can even put some color. I like red. So we'll do it in red. So we have here the absorbing boundary. And here you have a neighborhood, where if you start in this neighborhood, the time when epsilon goes to 0, and the neighborhood depends on epsilon, the time will not go to infinity because you can always escape very quickly. So this is a neighborhood, which is called a boundary layer. So we have here what is called the boundary layer, where the solution should go basically from 0, when you start exactly at the boundary, you are out in 0 time, to a solution that is inside that should go to infinity when epsilon goes to 0. Right? So this is the type of asymptotics or behavior that we are looking for. We say that if you start outside, wherever you start, it doesn't matter. It's a constant C epsilon that we have to find. Unless we start in this boundary layer, so this is x in omega minus boundary layer, or if you start in the boundary layer, well, now it should be a function of x. And again, to be determined. This is our goal of the next 20 minutes in dimension 2. and we will do it in dimension 3, and we will look at two holes, and then we will look at what happened when this is singular. That is, for example, you have a cusp. It's very hard for a Brownian particle to escape. Why? It's not that we are a bit vicious. Why it came out that you have to look at this. This was a model for crowding. You have a cell crowded with obstacles. What is important are the big obstacles. The small one is unimportant. And if you want to calculate how long it takes to go beyond in between those obstacles, they have to go through this funnel. And so if you now go to a regular, you put the obstacle on the grid, like this. So now you imagine that you have a square lattice grid. And as the radius A, and let's call it L, so A plus A is 2A, has to be less than L. But when 2A converges to L, you end up here with a small domain to escape. And then the question is, of course, how do you escape when you are in a domain where you escape at the end of a funnel? So this is different from this, where the domain is smooth. Here it will be like, suppose you have to escape on something with a cusp, which is really a singularity in the domain. So you should expect that the time to escape from here or to escape from there, although this and this can have the same length, it's going to be different. And we're going to see how it is different. And this is how we develop new type of asymptotic methods to solve the Laplacian type equation. And I want to explain this. But before, I promised two open questions. So let me give them to you. The first open question is, what is the mean first passage time for a Langevin particle? So what is a Langevin particle? So open questions. Now, this, what we're going to do is for this. Now suppose you have a Langevin particle. Wait, I have to maneuver this because now I'm getting hot. So 1 second. Okay. So what is the Langevin equation? The Langevin equation is, let's say, x dot plus second derivative plus gamma x dot equals, so let's say 2 gamma epsilon w dot. Epsilon is kT, gamma is the viscosity, the friction. In the Smolokhovsky limit, what is the Smolokhovsky limit? Smolokhovsky limit is gamma large, and then you can get rid of this term, this is well known, and then you get this divided by gamma, so you get 2 epsilon divided by gamma, which is exactly the diffusion coefficient. I'm not going to the Smolokhovsky limit. You have this equation. What is the mean first? What is the escape time? What is the narrow escape for this? I don't know. Why? Why it's more complicated? Because now you don't have if you are in, this is x in dimension 2, because you have velocity, you have to keep track of this position and the velocity, which means that you are in dimension 4. Because this equation is really x dot equals v and v dot, which is minus gamma v plus 2 gamma epsilon w dot, right? So now we are back to a system of first order equation, noise in one variable, not in the other one. And so now we have to see what is the associated domain. This is in x, now we have to see what happened for v. And then we need to give a proper boundary condition. in here. That is, the particle is escape when x equals 0, and v has to point out this direction. So there is here a formulation. I mean, it's not, I don't want to do that now, but we need to find out, first of all, the Fokker-Planck equation for this, which they are going to be a derivative in v and in x. We need to find the proper boundary condition for x and v, and then formulate. So we'll have probability. It's going to be the joint probability for x, v, and t, and then we need to find out what's going to be the mean first passage time. Probably we have to take the marginal of the whole velocity. We need to formulate this question correctly, which should take more than 5 minutes, and then see what's going to be the deviation. Obviously, in the Smolov-Hofsky limit, when gamma is large, we should recover what we're going to calculate today. But in general, they are going to be a perturbation. My question is, what is this perturbation? I don't know. Is this problem important? Maybe, maybe not.
Epsilon is not the same as the epsilon, the small parameter, presumably.
No, I'm sorry. No.
Call it D or something.
Yes. So this should be called, yes, absolutely. This is delta, right? Epsilon here, we don't care about it. So this is the same question than here, where we have this delta, and I want to know. So here we are going to have this expansion, and what I predict is that for the mean first passage time, for this problem, which we call, let's say, mean first passage time when we don't care about v, because we have to do some kind of averaging here, as a function of delta, should look like what we're going to get here, the c delta, plus probably there will be a perturbation in, I don't know exactly if it's 1 over gamma, or 1 over gamma with some power. I don't know what is the power here. Let's call it C1 delta. There's going to be an expansion. I don't know what's going to be the power here. But, I mean, what is exactly this? Would be interesting. Okay, so this is one thing. And now something that is useful in simulation is, I would like to, so this is open question Q number 1. Now let's ask question number 2. Again, we came out in the last 5-10 years. I had this question in the back of my mind because they pop up in some applications, and especially the question number 2 is what happened when we have a random walk. That is, if you think about, this is the continuous case. Now, in general, when you do your escape problem, you're on the computer, and the computer you're at a scale delta t. And so, what is the approximation? This is really the random walk. Xt plus delta t equals xt plus square root of 2d delta t here, and then you have your Gaussian variable at each step. It's we are introducing here a new time scale, a new delta t, which is the resolution of your simulation. Now, in the limit delta t goes to 0, this random walk converges to the continuous random walk in some sense. And so the question is that now the mean first passage time is a function of delta t. If you look at, calculate delta t here for a given, calculate the mean escape time for a given delta t. Of course, if delta t is very small, we expect, this is how you do your simulation, that it converges to this. Now, I don't know what is exactly the term, that is, it should be c delta plus something. Now, this I don't know what it is. Is it in square root delta, whatever?
Yes, it is.
What?
Yes, it is.
Square root delta?
Yeah.
Yeah, so it should be square root delta. And what is exactly the expansion here? I don't know.
Depends on the geometry.
Okay, so. That would be interesting to know exactly what happened. So let's call it F or C1 delta plus whatever. This would be interesting to see what exactly we have. Yeah, okay. Let's assume here we have not a cusp, because if we have a cusp, then it is very delicate. Because then when you enter into the cusp, the delta t, so we did a lot of simulation in the past, playing on this delta t, depending when you are. If you want to accelerate a simulation, you take, for example, delta t small when you enter in this region, and delta t large, so you make some type of hybrid simulation, so it goes very fast here because you don't care about exploring this space. And you refine it when you are close to the small hole. Okay, so this is something that would be that would interest us. I
Did you
didn't
do anything more clever than just making the time step smaller?
I'm sorry.
Did you do anything apart from just making the time step smaller?
It's adaptative depending on the geometry.
Yeah, but I mean, you can, because the problem is that your path can go out and then in again in your time step.
In a lot of what? Of this region?
Yes, exactly. I mean, out of the whole domain.
You mean what do you mean? If you have here reflecting boundary condition?
The time stepping can be exact,
Yeah.
statistically exact, meaning that you start from here and you end here, and that's the correct sample. Okay. The
Yeah.
problem is that your path in between can hit the boundary and come back in again.
Yeah. Okay.
But
We haven't.
So that's the problem.
Okay.
That's why you have square root delta t convergence.
Okay.
Okay. So the way to solve that is to have a correction, a conditional probability that you have hit the boundary, given your starting point and your ending point.
So you're saying that this term here will get mostly the boundary into this term?
Yeah.
Okay. Okay, this would be interesting, because then what happens if you have a strange, I mean, you need to have
Based on
some,
the geometry.
okay,
It's hard to calculate though.
but you have an expression? This would be interesting actually.
So if the boundary is
Flat?
flat,
Yeah.
then you can get the expression. And that's usually good enough to make the convergence, improve the convergence from square root delta t to something like delta t.
Okay,
But
All
if the boundary has a funny shape, then it's very difficult to calculate.
I see. Look, even if we have something flat, it will be already interesting. If we have like a round shape, this also be interesting. And then, of course, if you're in the biology, it's, we have all kind of strange, but already, with this kind of question, that's interesting. Okay. All right. So how do we solve this problem? So I told you last week that there are two groups, two approaches. One from my colleague in University of British Columbia that has developed match asymptotics, and us that have developed Green's function. I will show you Green's function. And match asymptotics, it's usually in the paper of the group of Michael Ward.
Dan Coombs is coming next week.
And Dan is coming. So Dan can,
Explain a little bit.
yeah, if people are interested. Yeah, this is what I've heard. It's coming next week. Okay, so how do we solve this question? We said we have to use Green's function. And how do we use the Green's function? We said last week we introduced the Neumann-Green's function. It's really the Neumann's function. And you remember this was something like Laplacian G equals minus delta. No, there's a minus here, delta at point P. And then we said that the first derivative has to be equal to minus 1 divided by ds, or let's say d omega. So we have the domain, we have a singularity at point P. The normal derivative here is negative. It has to be equal to this, because you remember we said that if you integrate this, you integrate what is the integration of the delta Dirac over the domain. It's 1. Integration of Laplacian is exactly dg/dn. So this is a constant. So constant, if you integrate over the surface, it is what we have here. So d omega, 1 over d omega multiplied by d omega is exactly 1 with a minus. So it's exactly 1 equals 1. So this is the only possibility. And g here is defined up to a constant. You agree? Okay. Now we have to use, so there exists, the solution is defined up to a constant. Now we're going to use this with the Green's formula. Okay, so we're going to express, now we're going to go from a partial differential equation to the integral equation. So now we have to use what is called the Green's identity. Actually, I can go up. So Green's identity is Laplacian J u minus G Laplacian u. If you integrate this over the domain omega, dv equals d omega u dj dn minus j du dn integrated over ds. Right, this is called Green's identity, and now we are going to substitute. This is a general identity. You should know how to prove this. This is basically the divergence theorem. Okay, so now we have to go slowly. What is Laplacian J? This is delta at point P. So this is with a minus. So this is minus u of P, right? Minus, so Laplacian u is equal to, so I am now starting from now, d equals 1. And we'll put it back later. We're going to carry all of this. Laplacian u equals minus 1. So minus and minus is plus, and then we have to integrate Green's function which is calculated at q, and I call it p, which is to recall the singularity, dvp over the domain omega, equals, by definition, dj dn is minus, so we have minus d omega, that's going out, and we have to integrate u, let's call it u of q, dsq, integration d omega, and now du dn, by definition, this is 0 everywhere except on the small hole. So this is now minus the integral of d omega only on the absorbing part, minus p, no, q p, and du dn. Calculated at which point? Point q, ds q. Can you see? What have we done? Just taking a PDE, transform it into an integral equation because of the Green's function. This is what the Green's function is telling us. How you convert PDE? Still, at this stage, what is u? We don't know. We just know that the value of u inside the domain is related to the value of this integral, the Green's function. This is actually a constant. You integrate whatever is u, and if u depends on epsilon, we can call this minus or plus, it's unimportant, but this is a constant that we call C epsilon. And this is something that's happened only at the boundary. You agree? Which is interesting now because the boundary is small, this is now where we are going to be able to say new things. But then,
sorry, this is absorption.
what?
But here the boundary is absorbed.
The absorption, that's right. But it's not u, it's the udn. It's the flux. It's not u. It's the udn, it's the flux. Yeah.
G is a Green's function or Newman's function?
J is what?
J is the Green's function?
J is the Neumann function.
Okay.
This is the solution of this equation. And we said last week that we gave an expansion. You remember, when you have a point Q that is close to P, there was a singularity. Right? Okay, we will use that in a second. So this is an identity. So now, if you knew du dn, we then would be able to calculate this. This, where u is in this integral? There is no u. Where is epsilon in this integral? There is no epsilon. So this, when epsilon goes to 0, what is the limit of this term? When epsilon goes to 0, it's independent of epsilon, it stays the same, it doesn't change. So when epsilon goes to 0, u should go to, u is the mean first passage time, it should blow up to infinity. So this will never compensate something that goes to infinity. Alright? So then we'll have this constant that has something that goes to infinity, and has also something here that might go to infinity. So, how do we get now information about du dn? On the whole, well, we'll get it from the equation itself. We need to have the conservation of the mass, which means, well, how do you get conservation? Let's integrate the equation, this equation, the first one. What does it give? So this is Laplacian u equal -1. Just rewrite it. Now let's integrate this equation. To integrate this equation over the entire volume, what is the integral of du dn? This is equal to du dn. The integral of Laplacian u by the divergence theorem is equal to du dn. But du dn is 0 except on the small hole. ds, and this is equal to how much? What is the integral of 1 over the entire domain? This is equal to the volume. You agree? So that's good. Suppose you are a naive first-year student, and now we have this. What can you say about du dn? Let's make an assumption. Let's assume, you would like to, if you are able to extract du dn from here, then we can get some expression using this. And this is exactly what we are going to do. It's not completely correct what I'm going to say, but I'll still use this. Let me remind you what we're interested in. We're interested in the escape time. It's a fundamental masterpiece of this entire class. How long it takes for a Brownian particle to escape through here, right? How long it takes, and how can we calculate this? So we said that we use the Green's function, we use Green's identity, and we are here, and now we are going to try to solve it from here, because if we can get u of p, we're in business. This will count only for order 1. This is a constant, and this is something that we want to explore. Okay, so now since we have a small hole, you have a domain, you have a small hole, and let's suppose, now this is where you see that if it is a cusp, it's different. Let's suppose it is a regular boundary. Regular boundary that, it is the meaning in geometry. This is like a piece of R2, right? Half of R2, let's say you take a disk, and you cut it, and this is really just by a small deformation, you can have it into this. So this is really something small. So we are integrating, so let's call it, I don't know, we can put here an axe of symmetry, let's call it minus epsilon and epsilon. I have to make sure that it's the correct notation. No, let's call it epsilon divided by 2 and epsilon divided by 2, so that the total length is epsilon. Now suppose I'm going to assume now something that is incorrect, but I will do this assumption, and it doesn't going to matter much. That du, suppose du dn, the flux, has a regular expansion. If it is a regular expansion, we can use what? We can use Taylor expansion. So Taylor expansion is at any point in this part here, we expand. So this is going to be a constant. Let's call it J0 of x, J0 plus J1 of x plus, and you do your Taylor expansion. Now if we plug this into this equation, integrating ds means integrating here over the length. So it's like integrating between minus epsilon divided by 2, epsilon divided by 2. Du dn, so we expand, so we can use the Taylor expansion, but it's really important. Because if you integrate with epsilon, you see that it's going to be epsilon squared, or even this one is going to cancel by symmetry, and you get something of epsilon cube. And this has to be equal to minus omega, which means that the leading order term, which is J0, so J0 multiplied by epsilon, plus other term that I do not care, has to be equal to this. Which means that the leading order term, J0, is minus omega divided by epsilon. So this is the first result that we get from here. And the leading order term of the flux, it goes to infinity with 1 over epsilon. All right, so this will give us this term. So now we need to use this equation, because basically now we have, although we have found this term, we will have another unknown, which is C epsilon. If you know this term and that term, when epsilon goes to infinity, if you don't care about this term, you will be given by the sum of the two. So now how do you get the information about the constant C epsilon? We're going to take u at which point? Now, what we haven't used here is the fact, where is the equation? Yeah, is the fact that we have used this, but we never use this. Now we're going to use this now. At P on the boundary, U of P has to be equal to 0. Now it's going to be exactly what we needed, because for P on this absorbing boundary, U of P equals 0. Then, at leading order in epsilon, this term will not matter, because this is 0, this stays whatever it is when epsilon goes to 0, which means that these two terms, they have to balance when epsilon goes to 0. So if we call it C epsilon, we have C epsilon plus or minus integration of d omega of the Green's function qp du dn ds. This has to be equal to 0. Can you see? And this is for p, so this is integration dq dsq. Now we need to calculate this. Now why this is interesting, and things can be done, because p and q now, p, this is in 0, so I call 0 here, sorry, p, it's in this absorbing part. So let's call the 0 of the domain, let's say the center. Now p, let's choose p exactly 0 here. Now q varies in this boundary. So p and q are actually very small. The distance between the two is very small. So, although the Green's function is something very complicated, the leading order term we know, because this is like in electrostatic. The leading order term in dimension 2 is log, And in dimension 3 is 1 over the distance, which blows up to infinity when P converges to Q. So what do we get? So let's do here dimension 2. Dimension 2 means Green's function, P and Q, equals, so you remember last week there was a factor 2 due to the image charge. There's going to be 1 minus pi log of the distance between P and Q, plus here a regular function which really I don't care. For the moment I don't care. Because when P converges to Q, this is regular, so this is finite. But this becomes infinite. And now we are going to put this into here and calculate this. And now, since we know what is du dn, which is the flux we just calculated, we're going to get C epsilon. All right? It took us some time to develop all the method. Okay, so now let's finish with this. So let's plug this into this equation. So the integral of the Green's function, which is, so let's call it minus and minus, this is plus 1 over pi. You integrate the same way as we did, it's minus epsilon divided by 2, integration of the epsilon divided by 2, log of the distance. So now let's call it the distance, this is the arc length, we can put it log of s. du dn, so again here, what I'm saying is not correct because, okay, never mind, I'll tell you later. Du dn, I approximated it as this, minus omega divided by epsilon. This is minus omega divided by, if I make a mistake, you just tell me, right? So 1 over pi log of s ds. Yeah, and this is this, and so this has to be equal to minus C epsilon. All right, so now this is clearly just one integral. By symmetry, this is twice the integral from 0 to pi over 2 of log of s. And log of s, what is the integration of log of s? Is s log of s minus s, something like this, right? Between 0 and epsilon divided by 2. And then we have to multiply by minus omega divided by epsilon. So this is minus C epsilon. So now in 0, this is 0. So we are left with epsilon divided by 2. Multiply by 2, so we are left, the 2 goes away, divided by pi, minus omega. There's an epsilon and an epsilon. And then we have log of epsilon divided by 2. Finally, minus C epsilon, so C epsilon equals, to first order, I don't care about the log of 2, because log of, when epsilon goes to 0, right, log of epsilon divided by 2, this is log of epsilon minus log of 2, so which is log of epsilon, 1 minus log of 2 divided by log of epsilon. So this goes to 0 when epsilon goes to infinity, right? So I don't care about the fact that it's a log of 2. So I neglect it. So this is minus plus log of 1 over epsilon divided by pi. Do you agree? Yeah, it should be okay. All right. Are we done or not? We have now C epsilon. So if we go back to this equation, what have we found? So minus U epsilon of P plus this Green's plus this term, which is really of order 1, equals C epsilon minus Green's function of P and Q du dn ds d omega. Maybe I have a minus sign somewhere now. No, this was minus C epsilon, no? Yeah. Okay, so now what happened if we take a point outside the boundary layer? If we take a point outside the boundary layer, which means the distance from P to Q is sufficiently long, you're not in this small neighborhood, the Green's function becomes of order 1. If the Green's function is of order 1, let's get it away outside the integral. This is something of order 1, a constant. I mean, not necessarily constant, but I do not care much what it is. So this is basically something that has to look like du dn over d omega a. So this, by definition, is equal to what? So I get this out. Du dn, this is what you just calculated to calculate the flux. This is exactly of the order of omega. So this is of order 1. All of this, when we're sufficiently far away, this is minus omega, which is really of order 1 compared to in epsilon, and epsilon is small. Which means that when you are far away from the absorbing hole, this is of order 1, and since the time goes to infinity, it should behave like u epsilon, and this is what we have. So u epsilon of p behave like omega divided by pi log of 1 over epsilon plus term of 1, which I haven't calculated here, which depends on the Green's function, the integral of the Green's function, other properties. And you can see that only in terms of order 1, you see the exit time, see where the particle started, not in the leading order term. The leading order term doesn't depend on the position as long as you start away from the boundary layer. Okay, so this is what we have in dimension 2, the mean first passage time for a small hole that is accessible. It's not a cut, there is no singularity. It's log of 1 over epsilon plus O of 1. Okay. And so I'm not going to work here, it's much harder to look at what is phi of x. Phi of x is something complicated that this is, you can take this entire function, which is true, and you try to make an expansion for this of u of p when p is a small neighborhood. And then the Green's functions start to contribute, so you cannot neglect as I did here. So you have to go and see how it depends on epsilon. But what is for sure, because it's a first order partial differential equation, du dn is not 0, and du dn, this exactly gives you the flux. Now I cheat a little bit, is that u, the flux, is actually not a smooth function, it has singularities. But in dimension 2, the singularity is not very drastic. So this is now one remark. So in principle, and this is known, the flux through a small hole in dimension 2, in dimension 3, in fact, I'll give you the expression in 1 second again for the dimension 3, the flux. So remark, the flux is singular, but it has a smooth, I mean, it's a gentle singularity. Actually, du dn is of the order of constant divided by 1 minus, or let's say epsilon square minus r squared divided by r squared. So there is a singularity when you go to the 0 minus epsilon divided by 2, so it usually does something like this. So I have approximated by a constant, but if you just use this in the expansion, and you expand around, approximate by r, by r equals 0, you don't care about this variation here. Because you're in dimension 1 over square root is integrable and it doesn't matter much. Dimension 3, it's a bit more drastic because it contributes much more, because in dimension 3 this occurs along a disk, meaning along if you have a disk as a small hole, it occurs along the length of the disk. Okay, so before we go to dimension 3, let me ask you a question. All right, everybody wrote, it's okay, I can continue? Okay. So now let's discuss what happens if you have two holes. If you have n holes. So now questions. What is the mean first passage time if you have a domain and you can have n holes? Let's say we start with 2. What is the mean first passage time to exit? You start from x when you have 2 holes. There are 2 holes. Is it the same as the mean first passage time with 1 hole? So, what is the intuition? And then once we understand the intuition, we can write the equation and we will see how to solve. All right, we discussed the mean first passage time with 1 hole. We found an expression for it, right? Because here, this is the mean first passage time for 1 hole. Now, if you have 2 holes, what do you expect? So, if you start, let's suppose you have 2 identical holes with the same length epsilon. How long it takes for a particle to escape? Well, the intuition is to say that if you have 2 holes, the time would be the time divided by 2. The time we found for 1 hole divided by 2. This is true as long as the 2 holes are well separated. So what happened now if the 2 holes start to become closer and closer and closer again? So let's look at the magic of this. This is the time for 1 hole, which is pi divided by omega, surface divided by pi log of 1 over epsilon. This is for 1 hole. Now, we said that for 2 holes, the time for 2 holes should be when they're well separated, the time for 1 hole divided by 2. I haven't proved this yet. Now, if 1 hole is moving to the direction of the other one, what happens when it becomes tangent? So they are really like forming a single hole because they are really the 2 together. So what is the size now of this hole? Is twice the size of 1 hole. And now we just calculated it. And we said that the size, the time for a hole of size 2 epsilon is going to be omega divided by pi log of 1 divided by 2 epsilon. But now log of 1/2. This is nothing compared to log of epsilon, because this can be also written and write this log of 1/2 plus log of 1 of this, correct? When epsilon is very small, you don't care. So when the 2 holes are very close together, the time is the same as the time for 1 hole. So in general, when you have 2 holes, depending on when they are, you can have a factor 2. If they are very close together, it's almost, of course there's a correction, there's something, it's almost the time for 1 hole. And if you start to move them apart, it starts to be divided by 2. And why we were interested into this? Because in bacteria, you have exactly receptors on the surface, and sometimes, under some condition, the receptors start to cluster, and sometimes they can get uniform. Now you can ask, how does that affect the flux? How? Because, okay, what is a, let me back up 1 second. You have a, whatever your cell, how it senses its environment. I'm not talking about the eye where you have photons that come directly, but usually, like a sperm, a cell in the environment, they sense what you have outside because they have small receptors. And small receptors, let's approximate them as just absorbing. That is, when molecular arrive, it is absorbed. It's not fully absorbed because usually it binds and there is some kind of pathway that then lead to some signaling, but basically you have this. So you sense your environment because some proteins arrives. Most of the time they are just reflected. But then you can change the flux here by looking at by having different kind of configuration. You can imagine two extreme configurations. All are clustered compared to the case where they are all, let's say, uniformly distributed. Now the question, how much you sample, what's the difference between the two? And it has been observed in some bacteria that this is exactly what happened. Under some high concentration of whatever cues or chemoattractants, you have the receptors that are sometimes uniformly distributed, and in the other extreme, they can get forming a single cluster, or they are clustering. So then this is a way to modulate the flux by changing the position of your absorber. So we wrote some papers about almost 10 years ago, 2006, 2007, yeah, 9 years ago, on this. And now how do you prove this? The method should be exactly what we have done. What is the difference? So let me erase this. How do you prove all of this? So it's clear to understand what I said in dimension 2. In dimension 3, it's more subtle. Why? Because in dimension 2, having two holes and then bringing them together has the same geometry. That is, they are together, it's one hole with double size. Now, what is the equivalent? Now you suppose you're in dimension 3, you have a disk. And now the disk coming together, there is no like shape for two disks. What is the equivalent shape? Is it a disk of size r with a certain factor? The answer is no. There is no such equivalent. Why? Because the mean first passage time sees the shape of the hole. Not in dimension 2, because it's too simple, but starting in dimension 3. What does it mean it sees the shape? Okay, let me explain this because I think it's important before we continue. I haven't discussed yet dimension 3, but the mean first passage time in dimension 3, if you have an elliptic hole, it does depend on the elliptic integral of the characteristic of the ellipse. Something like KE divided by A. So if you have, you have an ellipse is characterized by two axes, A and B, and so K of E, something like integral of 0 divided by pi over 2, this theta, something like 1 minus, so if A is the biggest, something like this, A divided by B divided by one of them, cosine or sine, maybe it's unimportant, something like this. So it does see the shape. You don't have here something that, you have here something that depends on the fact that you have an ellipse. And the matter of fact is that actually an open question is what is the escape in dimension 3 for a general shape window? Nobody knows. We try very hard a square or a rectangle, very hard. And we found a new type of flux. Why it's hard? It's hard because you have singularities here. And at the corner, the same that in here in dimension 2, you see, there is a profile of the flux. At the corner, at the singularity, here you get a lot from the corner. So if you neglect them, you're screwed up. And it's very hard to calculate the flux at a corner. And the singularity, especially in dimension 3, you don't have conformal mapping. It's tough. Okay, it's not an easy question to understand in dimension 3 when you have receptors. What is the equivalent receptors? What are the equivalent shape? There is none. So it's much harder to compare with the dimension 2 case. Okay, so I'll give you this equation and then we'll be ready for a break. So how do you now solve? Now suppose this is the exam time. Except that it's going to last 15 seconds. How do you solve this question? How do you, I gave you all the methodology. How do you now solve the mean first passage time for 2 holes? Answer. 5 more seconds. The answer is, let's use what we have done. Except that now we are going to write this equation. Instead of having this at 1 hole, we'll have it at 2 holes, and that's it. And now we're going to have, so let's write it, right? So now instead of having, this stays completely valid. Now I'm just writing this. How do you write this? This now is going to be written with 2 terms because we have 2 holes. So this is hole number 1. So this doesn't change, doesn't change, doesn't change. This change. So this is hole number 1. Let's call it omega 1. JQP du dn minus integral of dA2 Green's function du dn, the same thing. Now, we're going to have, before we had 2 unknown, there was du dn, and the constant c. Now we have an additional unknown, there are 2 fluxes, and c, so there are how many unknowns? There are 3. 1 flux at 1 hole, 1 flux at the other hole, and c. Last time we had 2 equations, now we need 3 equations. So where the equations are coming from? Now if we integrate du dn, so we had Laplacian u equal -1. So we integrate this again. So this is Laplacian. So I integrate this, we integrate this. This is equal to minus the volume. And now if we integrate du dn over the absorbing part, now it's divided into 2. There are 2 holes, so this is du dn d omega 1 plus du dn d omega 2, which has to be equal to minus omega. So now we have 1 equation here, and now we need 2 more. Where are the 2 equations are coming from? We are going to take u at a point P, where P belongs to 1 hole, and then to the other one. And this will give us, through the Green's function, the correlation. So the correlation is going to be hidden in the Green's function interaction. Okay, let me write this. I write the equation, and then we can break. So take u, P, for a point P, for hole number 1. Let's call it 1. This is equal to, by definition, u is equal to 0. This, we say we don't care, because this is of order 1. This is a constant, and now we'll get this. So for this we get minus c epsilon equals 0. So 0 equals minus c epsilon minus, so now we are integrating for P in A1. So let's call this point P1. So let's call it Q P1 integrated over whole 1 du dn minus d omega 2. We have to integrate Q for whole number, let's call it P the same, P1. And now this is dp du dn. And now this is ds p, the dsq. And this is dsq. Right? So this is, we wrote it once. Now let's take a point P for the whole d omega 2, and let's call this point P2. So this is P1, this is P2, so this is 0 minus C epsilon minus Green's function Q P2 at whole d omega A1 du dn ds minus Green's function at point Q P whatever, P no P2 du dn dsq. Right? Now we have one equation, two equation, three equation. What are the unknowns? So let's call the unknown the flux. Du dn at whole number 1, let's call it C1. Du dn at whole number 2, A2, let's call it C2. So we have C1, C2, C epsilon. We have three unknown, three equations. We are good. And now this is elementary matrix equation. Why? Because, all right, so let's just discuss the equation. I'm not sure I want to solve them now, but it's possible. I mean, the same way we did. But just to show you what we have. And this is the interesting part, because all the geometry we have discussed is contained in the Green's function. This is whole number 1, this is whole number 2, and they are small. So what is this term here? This is Green's function at point P1 for Q in this hole. So you vary in here, so this has a singularity. Now this is now Q varying 2, and P is in 1, and it varies really in a small position. So this is almost constant. Doesn't vary much, this distance, which is the distance here. So the Green's function here, as you remember, was written, it depends on the distance between P and Q. So here this is a dependency on the distance. If you're far away, and if J is about constant, because this distance doesn't vary much, we can take it out, because it's a constant. And then you have to integrate the flux. And now this is completely symmetric. So I don't have to discuss this, this is the same. So now you just can take it out, and you end up with a system of three equations, three unknown, and you solve. And you get the mean first passage time. The mean first passage time is C epsilon. If you're interested, this was published with myself and Shoes. This is, I think, 2007 in Phys letter 8, almost 10 years. And then we have a long paper, the same in Journal Physical A. I think it was 2008, because it takes usually more time to be published in that journal than in that journal. That's the reason. This is important again, because of this notion that you can regulate fluxes by positioning. I can tell you one more thing, that, for example, today what we are looking at is that suppose you have a source here, and you have some receptors. Can you find where the source is located? If you can just calculate, or you are just able, you sit on here, you ask your wife or whoever you want to sit on this one, and you sit on the other one. And if you have children, they can also sit over there, and they count. And at each moment of time, you are at home, and you ask how many particles you get. how many particles you get here, how many particles you get here, how many particles you get there. Can you, from this, tell me, all right, we have to move, here is the target, it is there with a given distance. It's not, it hasn't been solved, although this is really what should have been solved when people talk about chemotaxi. Because this is not about how many molecules are fluctuating at this place. This is the ability of the cell to know where is the source. And this is much harder actually than what I showed to you. But because it involves Green's function for outer domain, not inner domain. All right, so it does matter the number of receptors and where they are located. We'll break now. I'll explain when I'm coming back, when we come back, dimension 3. I leave this, so if you're interested, you know, we did this calculation in these papers with many holes. What Michael Ward, my collaborator and competitor, I have to say my friend, has done something a little bit better than us. He has calculated the expansion, the full expansion. So he has, because he's using this match asymptotic, he could get not only the leading order term here, but the next term. And this is interesting, because then you can see how the position in the mean-first passage time, you see basically why in dimension, if you do the mean-first passage time here, why you cannot reconstruct. Because this term is occluded by that one. But not outer space, because the outer space, the mean-first passage time is infinite. So this is what he has done, and it's a completely set of papers that are also very interesting with a different method. Okay, so let's break, and when we'll come back, we'll discuss the bit dimension 3, and then I want to show you the completely new type of asymptotics of partial differential equation, which are based on conformal mapping to solve the exit problem in cusp, when you have cusp, singularities. 10 minutes break.